The following session is titled Embracing the Quadrivium as Christians in the World. Mr. Nathanael Hahn teaches 6th through 12th grade classes in math, science, and music theory at Mount Hope Lutheran School in Casper. You can learn from him and the rest of the faculty by visiting bach2church.org, and that is VACH. Please welcome Mr. Hahn.
Thank you. Can everybody hear me all right?
No.
All right. My presentation is essentially, I'm going to make the argument for teaching the mathematical arts as inherently Christian things. I'm also going to give some practical ways that we can make that happen. As Lutheran teachers, our goal is to give our students an education centered on Christ and His Word. Furthermore, we want everything we teach to be entirely Christian, not merely Christian flavored. But there exists a potential problem, I think, in the way we approach Christian education, and is closely related to a commonly used phrase in education. Who here has heard the term faith integration in reference to education? I've heard it a lot, not here, but other places. So on the surface, the idea of integrating our faith or integrating Christianity into what we teach sounds like a virtuous goal. Don't we want our children's education to be saturated in the truth of God's Word? The answer is yes, but that goal is not accomplished by so-called faith integration. Indicative of this is the fact that trying to use Jesus as a mere ingredient becomes a chore. It feels unnatural, and most notably in math, it seems almost impossible. How could you go about integrating faith into a math curriculum? A couple of appendix lessons about creation or the golden ratio, a problem about pairs of animals going into the ark. Because of this perceived impossibility of putting Christ in math, math seems to be the one subject that we, more or less, teach the same way secular schools do. On the contrary, I don't believe that we, as Lutheran teachers, actually have a duty to integrate our faith at all. Trying to do so concedes the lie that what we teach is by itself foreign to Christianity, and if it is indeed devoid of Christ, it doesn't belong in our Christian schools. Jesus is not a steroid you can use to bolster a curriculum. On the contrary, I will argue that math is inherently Christian. It's ours. In fact, I believe that all the liberal arts, along with history and science, naturally spring from our life in Christ. Although you likely already believe that too, I think we still do well to examine every subject we teach in light of the gospel and determine how the content we teach is Christian, because that knowledge will inform the way we Christians teach. This presentation will be my attempt at showing how the four mathematical arts, arithmetic, geometry, music, and astronomy, are Christian through and through, and that studying them, and therefore teaching them, is something wonderfully edifying for any Christian. I'll also share some practical ways a math teacher could implement this kind of thinking in his classroom. Before I begin, I want to note that I largely see this presentation as a way to open the door to more conversation about our educational philosophies, our teaching methods, and our understanding of what it means to offer a classical Lutheran math education. I should give you a definition for mathematics, but before that, we need a definition for what it is to be human. We've already had great definitions from multiple speakers, but I'll give one here as well. We can't hope to teach any subject in a thoroughly Christian way if we don't have a thoroughly Christian understanding of who we are. After all, both teachers and students fall into the category of human being. So, what is a human? I'll offer a rather profound definition I've unabashedly stolen from Dr. Gregory Schultz. Human beings are the same species as God. Don't worry, I'm not a Mormon. I'll explain. This definition describes two major parts of human nature: a capacity for language and an identity in Christ's incarnation. First, being the same species as God means that our identity is inseparable from the incarnation. As Lutherans, we understand that what we are is the very thing God needed to become to save us. God the Son became the actual flesh and bone, body and soul, language kind of being that we are. Because of Christ's incarnation, death, and resurrection, we can easily understand how our children are people of infinite worth. I'm sure you don't need convincing on that point, but it's worth saying. Seeing students in the light of the gospel is absolutely vital to how we choose to educate. The gospel necessitates that we do not educate our children merely to become firefighters or veterinarians when they grow up. Rather, we educate them to be who they are already called to be in their baptism. This is the vocation of being Christian. The gospel also necessitates that we understand creation's order and harmony as sustained by our loving Savior. Not for his own personal enjoyment, but for our sake. In him all things hold together. Furthermore, we know by the gospel that Christ's beautiful order is also continued forever in the new heavens and the new earth. This is an order that we can trust because we trust in the God who orders it. In light of the incarnation, being the same species of God as God also then means that we are language beings made in his image. Unlike any other creature, we have the God-given capacity to reason, converse, self-reflect, even think about our own thinking. No other creature has this capacity. We can see that language is part of the image of God when we look at how he acts. Through Christ the Word, the entire universe was created by language, and it continues to be sustained by that same Word. God also speaks to us humans today through his Word, creating us anew in baptism, teaching us his will, and giving us his eternal gifts of forgiveness, life, and salvation. It's rather extraordinary that we get to be the creatures who can hear and speak the very means by which God provides life. We can't overlook the fact that we are now fallen, that our human nature is corrupt. Yes, we still have that language capacity to reason and think, but it's been thoroughly twisted by sin. We cannot trust in our reason. We even misuse it by lying and deceit. We even deceive ourselves. Rather than trusting in our own language and reason, we can only trust in the Word of God, the Word that humanity throughout time has always desperately needed. The fact that we are language beings also means that language is the atmosphere in which we live and think. We can't have meaningful thoughts without language. You can test this yourself. You'll find it impossible to think something without thinking in English or Latin or some other language. You can try it. Can you have a thought without thinking words? I don't think you can. It may seem a strange philosophical idea that our atmosphere of thought is language, but I think it is a Christian one, and one that becomes essential to the way we teach any subject in our classrooms. Given these two parts of being human, that is, being language beings and being redeemed by Jesus, the God-man, we can begin to formulate how best to understand the content we teach and how best to educate our children by it. Because our definition of being human is based on language and the gospel, I will provide a corresponding Christian definition for mathematics. This is what I have on your handouts. Did everyone, I know not everyone had a handout. Was everyone able to at least see one? Is someone next to you? Okay. Here's the definition. It's the art of navigating the order and beauty of creation through language and wonder. I'll explain. Since we are language beings and can't make sense of anything without language, it only follows that for mathematics to make sense of the world, it must be, in some respect, understood as linguistic. If math were not linguistic, it would be useless to us as a rational tool. This is why we should teach math through language. And by language, I mean like English, Latin, actual languages. Because of the gospel, we know we'll live forever in God's orderly world. So in studying that order, we are wondering at eternal things. Furthermore, in the gospel, we have the freedom to wonder about the world without fear of what we may discover. If we were pagans, we would navigate the order of creation with the underlying fear that utter chaos is only a few steps away. Pagans fear death, and the ultimate goal of science for them is to achieve immortality, fashion the elixir of life, if you will, or evolve past death. And they do this to escape that chaos. On the contrary, we know that death has been defeated by Christ. We know that the world is not owned by chaos. Creation is ordered, and it's ordered by a God who loves us and who has given it to us to care for it, fill it, and subdue it. Mathematical order is God's, and in Christ it is ours. This knowledge leaves us free to navigate the world of order and beauty without the fear of impending doom. This is why we should teach math through wonder. Alright, so I'll start talking about math now. First by describing wonder in mathematics and how one might put wonder into practice in the classroom. And then I'll move on to language. So we're doing wonder first and then language. When I say that math should be taught through wonder, I mean to use the word in two senses. We could call the first type of wonder the why type of wonder. This wonder is best exemplified by the persistent child who uses a familiar Socratic technique. I'm sure you've heard this. Why does my pencil fall when I drop it? Because gravity pulls things down. Why does gravity pull things down? Because the Earth is massive and massive things have more gravity. Why? Because space is curved by massive objects. Why? Why? You can keep going. You get the idea. This why type of wonder is born out of a God-given curiosity about the world over which we have been given dominion. It's the type of wonder we mean when we say, I wonder, fill in the blank. It's a thirst for knowledge. It's wondering about. Now, continue that conversation with the child, and you probably know from experience where it leads. You need to put an end to the persistent whys by answering, because God made it that way. It may be a useful rhetorical tactic, but that answer does demonstrate the second sense of the word wonder. When you wonder in this second way, you do not continue to pry into the matter, but you stop asking questions and simply stand in awe, submission, and delight at the beauty Christ has made for you to enjoy. Now you're not wondering about something, you're wondering at something. This type of wonder is necessary for the curious Christian to have, because there comes a point where more knowledge does not necessarily constitute good knowledge. More on that later. I will get to it later. We could call this second type of wonder, I apologize for the trite, this is the tritest thing I think I've ever written, but it's we could call it the wow type of wonder. This is a particularly Christian kind of wonder because Christians are in the business of dealing with incomprehensible mysteries. And we are well acquainted with the doctrinal dangers of prying into them. On the other hand, we are also well acquainted with the joys of possessing those mysteries and accepting them as such. So, we have two kinds of wonder, wondering about and wondering at, and both come into play when we deal with the mathematical arts. Furthermore, I believe that the mathematical arts are, or at least should be, particularly responsible for increasing a student's capacity to wonder. Let me explain how each of the four mathematical arts, in its own unique way, teaches a student to wonder, and I'll also explain how we all can teach it in the classroom. So, first, arithmetic. Classically speaking, the study of arithmetic means strictly the study of number. That is, the natural numbers we use to count. It involves observing the relationships between numbers, extracting their factors, discovering the patterns within them and between them. It also includes a study of the four operations in mathematics: addition, subtraction, multiplication, division. A fantastic primary source for this type of thinking is the Introduction to Arithmetic by Nicomachus of Gerasa. Nicomachus begins by outlining the nature of the quadrivium, moves to numbers themselves, and proceeds to delve into the thriving, complex ecosystem that is arithmetic. In case you've never picked up the work, I've included one little example from the beginning of his work in your handouts. So this is that enigmatic series of numbers. Sure, I'll actually, can everyone see it, or would it help if I do this on the board? Yes. Okay. So the sequence goes like this. You've done math, probably will recognize it. He calls this the even times even series. So what he does here is he lays out this pattern, and then he starts describing, okay, what are different patterns I can see in this? I'll give you a couple, because they're pretty cool. Can you all see this? One he points out is, if I take, say, I want to stop at 8. If I take all the numbers before that and add them up, so 1 plus 2 plus 4 plus 7, you always fall one short of the number that you're getting to, so plus 1 is 8. Choose 64. 1 plus 2 plus 4 plus 8 plus 16 plus 32. If you do the math, you get 63. Wow. That's cool. this is just as cool, I think. You take two end numbers. So say I want to start with, let's say I want to go to 128. So I take 128 and 1, and then 2 and 64, and then 4 and 32, and then 8 and 16. They're all going to, well, let's see, add or multiply?
Multiply.
Yeah, multiply. Yeah, I am a math teacher. They all multiply to be the same thing. And this works for, I could go to 2048 if I wanted to. It works. So, I mean, these are kinds of things we can show our students, even at lower grades. They'll think it's pretty cool as well. So, we mathematicians in the room could just explain away these patterns with a more transcendental practice like algebra, or simply write the series off as the powers of 2. Many of you probably are already familiar with these kinds of patterns in this series. But there's a unique kind of magic in discovering numbers for yourself or having them uncovered for you. Here we have a prime example of wondering about, the why kind of wonder. The patterns I just mentioned only scratch the surface of this sequence. There's so much more to be found. Here, but also in all numbers. Just ask someone who studies number theory. They'll tell you there is a lot just in arithmetic to understand. It's the playful curiosity of a student thoughtfully clicking away at his calculator that the study of arithmetic fosters. Yes, there are math facts to memorize, but if arithmetic has become only rote memorization, we teachers have work to do. We should convince and inspire our students to explore the world of number. So that's arithmetic. Second, geometry. This mathematical art encompasses all study of lines, circles, polygons, solids, and shapes of even higher dimensions. But also fundamental to classic geometry is the study of magnitude, that is, divided lengths. So literally, if I take a length and divide it, that would be a magnitude. While the ancient Greeks did not conceptualize irrational numbers like we do today, they did encounter them in the form of distances, areas, and volumes. Thus, we could properly include irrational numbers and even improper fractions in the study of geometry as well. One example of this might be familiar to one of you. Like if you draw a square and say, I make all the sides be 1 unit long, the diagonal, you get square root of 2. So that's one example where you really get irrational numbers from working with geometry. If we had to assign a primary text to exemplify the art of geometry, we would have to choose the fan favorite Euclid's Elements, simply because it's a time-tested excursion into the world of shapes and measurement. Euclid shows us very plainly the ability of geometry, like arithmetic, to train us in wondering about. From the very first proposition, we are forced to experiment with circles and lines to synthesize a simple polygon. While one could read through the proof, there's a particular excitement that comes from hunkering down with a compass and straight edge to alchemize a new geometric idea for yourself. A geometry teacher, like Euclid, should foster in his pupil patience, particularity, pithiness, and most of all, a playful yet insistent curiosity. Arithmetic and geometry are two arts that naturally teach a person to wonder about. They train him how to find out for himself the beauty God nurtures in the universe, to peer into it, to ask questions about it, and to think logically about it. They sharpen his God-given reason. The other two mathematical arts, while they do share a wide type of wonder with arithmetic and geometry, also especially teach us the other type of wonder, how to wonder at. Music and astronomy have a peculiar way of showing us beauty without requiring much knowledge, and that makes them vital to nurturing wonder in students. Music, and then I'll get on to astronomy, music largely deals with ratio and proportion. It measures one number up against another and quantifies the relationship. In my opinion, the study of ratio is very core to a thorough understanding of mathematics and key to many, many different things, especially in seeing mathematics beauty. Ratio is vital to why music even sounds good to us. Limiting music to the written ratio only, however, does music a great disservice. It also includes, of course, the tunes and harmonies we hear with our ears. There's probably no greater way to experience the sheer beauty of God's mathematical order than to listen to great music. A chorale by Bach, or a mass by Pretorius, or a tune by Kruger unveils in plain sight so much of what algebra or calculus take years to reveal. This is why music teaches the wow type of wonder so well. In order to see mathematical beauty, a student listening to Bach need not numerically analyze the structure of his chords, the cadences of his phrases, or the overtones in his instrumentation. Although doing so often uncovers even more beauty, music theory is its own microcosm of beauty. Giving our students great music to hear and to sing teaches them to recognize beauty when they see it, and it teaches them how to wonder at beauty without the need to ask why. Some things God has put into the world simply to be enjoyed by his children. I should add that we Lutherans have a unique blessing for our schools in the tradition of hymnody. Great hymns show the beauty of the doctrine they contain in a peculiarly simple way. Great for all of us, but especially useful in teaching kids. If there were ever an art whose hallmark was wondering at, it would be astronomy. Only until recently, astronomy has given man something with which he can do nothing but stand, look up, watch, calculate, and predict. Every other science allows man to get a hold of something, to pry away, or to investigate. I'm not saying that scientific investigation is a bad thing by any means, but investigation without an awe for creation leads to ghastly methods, absent of moral discretion. Science which knows no bounds becomes a twisting of creation to the will of man, a rack on which nature is stretched, the kind of dark magic from which Tolkien's Uruk-hai are born. Humanity has obtained forbidden knowledge through science ever since Adam and Eve learned good and evil. Cain discovered what it takes to kill a human. Nazis observed the limits of human pain. U.S. doctors pioneered hormone replacement theory. Some might argue that the atom bomb was something meant to remain undiscovered. The list goes on. Mathematical and scientific knowledge can and should only reach so far, because our human reason is fallen. Our reason can't tell us about beauty, or morality, or spiritual matters, to name a few. And to paraphrase the philosopher Wittgenstein, whereof science cannot speak, it must remain silent. There are things science simply shouldn't seek after. Astronomy can help students see the joy in not scientizing too far, keeping a spaceship view of science in a world of space probes, if you will. In the way it uses wonder, astronomy can be a paradigm for Christian scientific discovery. searching the deep fractality of the night sky, can easily show us just how much care and detail God has put into the world, and no doubt how much He will have for us in the world to come. In these ways, our four mathematical arts lead a student to wonder about and to wonder at. How to implement each art in the classroom, I'm still working through myself, but I have come up with some potential ways we can practically apply an education of wonder into our math classrooms and by extension our science classrooms. I suspect most of us already implement many of these ideas, but to be aware of the avenues to Christian wonder is important. One, and I'm following your outline here so you can follow along there. One, during math instruction, don't be eager to shoot down student answers that aren't as correct as expected. Incorrect answers are often actually incorrect, but occasionally wrong answers arise from alternate mathematical understandings that are as equally valid as the curriculum's explanation. I'm not being relativist here. I'll give you an example. In one elementary class, I was teaching how to add fractions by finding common denominators. I can't remember the exact ones, but if I did, say, 1/5 and 1/7, and we're trying to add these, and I asked my students, okay, because they're already familiar with adding fractions, and I said, okay, in my answer, which one of these should be my denominator? And what would you expect the answer to be? Neither. Yeah, that's what I was expecting. One of my students, and I'm happy she did this, she said both. And at first I thought, okay, that's not right. But then I thought about it for a second, and I thought, she's actually right. Just not in the way I was thinking. Because you would essentially have a denominator that does use both of them, just as fractions, right? So I thought that was fantastic. That's great math right there. I've used that way of speaking ever since because it's an incredibly intuitive way to see that problem. It literally came from intuition. Okay, so we should avoid shooting down wrong answers too readily, but we should also avoid giving right answers away too readily. We need to give our students ample time to brainstorm solutions, wrestle with problems, and practice using the curious side of their wonder. Students need to understand that math is an art of discovery and exploration, not just a collection of definitions and methods to be learned. They can experience this freedom if they are given time to have their own ideas, and if these ideas are, and they need to know that those ideas are taken mathematically seriously. In the end, of course, our job is to present the correct answer or the most efficient method, but cultivation of wonder is still necessary. I've found that in either case, whether my students are right or wrong, it's incredibly valuable to me and to them if I just ask them why they answered the way they did. Number two, in the same vein of encouraging curiosity, during class we should also be open to going on mathematical tangents when students ask questions out of curiosity. You'll probably agree that these kinds of questions are generally rare in a math class. Usually they just want to get done with the lesson. But we should use those footholds whenever they come up because they help students feel the reward of creative mathematical thinking. 3, use actual examples of mathematical things that happen in real life. I found that students greatly appreciate a well-constructed real-world problem. They like to know that we teachers do in fact care about practical application. For instance, I could give a problem about cutting up pizzas during our pizza lunch instead of giving one about going to the store for 100 watermelons. Robust real-world problems also show students what it's like to have natural mathematical intuition that wonders about the real world. Often, the casually pondering mind is much more mathematically capable than the one that's hard at work. The mathematician Henry Poincaré made the argument, and I paraphrase here, that the best mathematical creation comes not from several hours of cognitive grind, but from the sudden revelation of a well-trained intuition. I believe that's true. By the way, I still think having fun problems is important too. It's okay to have problems about 100 watermelons. I think that's fun. Number 4, I believe that if a teacher doesn't exhibit the wonder he is trying to instill in his students, he'll fail to instill it. Therefore, it's important that we as teachers keep the wonder alive for ourselves and pursue it. First and foremost, I think we should read the primary texts of Western mathematics. I'll get back to that. But we should also find other fun avenues of mathematical learning. Reading through mathematical textbooks is not always my idea of fun, so we need other avenues as well. This could be anything from watching quality math videos online. I've actually got a few channels up there, maybe you've heard of them on your handout. They're fantastic. So watching videos like that to more mundane things like finding the most space-efficient way to arrange tables for Thanksgiving dinner. That will get you your math badge. So keep math fun for yourself. We can't speak of wonder in mathematics, especially in astronomy, without also touching on science or natural philosophy as an art, because math and science are so interwoven. The wonder of math can inspire wonder in science and vice versa. So briefly, here are some ways a teacher might apply the same philosophy in his science classroom. As in math, the teacher should not be opposed to divergence from the original subject matter if it means feeding student curiosity. Not all the time, but occasionally it's very helpful. Of course, classes have time restraints and we have content we need to teach, but a measure of freedom can be granted to students to let their minds wander. We can let them ask tangential questions, even dive a little into a different area of science to quench someone's thirst for understanding. Sometimes I'll even keep a list of the class's curious questions on the board to research and answer for myself before the next class. To keep with the astronomy paradigm, we can be willing to turn the telescope, if you will. Doing so encourages that exploratory wonder that is distinctly Christian. Number 2 for science, whenever possible, avoid merely telling or reading the scientific facts to students, at least doing so excessively. Doing so excessively will turn science into a chore, and it will kill the spirit of discovery in most students. Science isn't primarily done on the notebook, it's done in real life. That means students should be led to new information either by guided classroom discussion and logical thinking, or by demonstration and experimentation. That brings us to number 3. Make science class as observation heavy as possible. In biology, find as many physical specimens as you can get your hands on. In physics, show physical phenomena to students, even show them how the equations work physically. In geology, go for a hike in a place where cool rocks and geological formations can be seen. In chemistry, try to get the actual chemicals even in lower level courses. These times for observation don't necessarily need to be times of rigorous note-taking. They don't always even need to be experiments proper, although we shouldn't by any means neglect teaching the scientific method. All of this should be done in the spirit of astronomy, that we are here to see the fascinating order and beauty Christ maintains in the universe. All right, back to math. We've covered wonder, the first side of Christian mathematics. But what about the other side, namely language? As I said before, in order to make sense of the world, we need to use language. So, in order to make sense of math, or make sense with math, we also need to use language. The result of this necessity is, I think, twofold. First, we Christian math teachers need to prioritize content over method. Classical education works so well for a Christian education because we seek truth, and truth is found in content, and classical education is all about content. Math should be no different. The content, or truth, in each mathematical art is found in language, the actual spoken or written word, not in symbology. Symbols are highly useful, but they always represent words, and words are that of which truth consists. For example, if I teach a math class on ratios and demonstrate to students how to fill in a ratio box correctly by this or that method, I've only taught them an empty method. On the other hand, say I give them multiple examples of what a ratio is. Perhaps taking 8 boys and 4 girls in the class, and then dividing them into groups of 4 and 2, and then dividing those same kids into groups of 2 and 1. And exploring the relationship between those ratios. Then, if I do that, I have begun to lead them to understand what a ratio actually is. This is concrete truth. It's part of the way God works. This isn't to say that students won't eventually understand the nature of math by rote practice, but many more students, I've found, will understand it if you just tell them or show them outright. Method is important, but method is not content. We ultimately shouldn't teach math to teach the how-to. Insisting on one method clouds the mathematical mind. Instead, we should focus on the what. I've had many students, and you probably have too, who have raised their hands to ask the question, how do I do this? With the expectation that they will be reminded of this or that method. You could tell them a method and they get through the problem, but doing that leads the student no closer to the truth of the matter, to the nature of the concept. For example, SOHCAHTOA can get you through a trig problem, but it can hinder a holistic understanding of the beautiful nature of trigonometry, vectors and circles, as well as the connections between all those. Cross-multiplying works extremely well, and it's a great tool, but it can become a crutch that causes students never to understand what proportions actually are. To use an analogy, taking the freeway is easy and effective and efficient almost all the time. But you'll never learn the lay of the land or the beauty of the countryside if you always take the freeway and never the slower, winding country roads. And if there's an accident on the freeway, good luck making a detour if you don't know the lay of the land. If students are taught primarily man-made method and not actual truth, they have a point when they ask, when will I ever need to use this? Or why do we need to know this? After all, a method is a mere algorithm, something you could program a computer to do. Our reason for teaching math is not, well, if you're in the grocery store, what if you're in the grocery store without a calculator? If learning how-to were the main drive of math class, we might as well write computer programs instead of teaching algorithms to kids. Certainly, students should be taught how to compute, but they shouldn't be turned into computers. If students are, in fact, taught the actual content of math, such as the true nature of ratios, or the reality of multiplication facts, or the physical meaning of integrals, they are doing something unique to humans, namely, working in language. They are learning to talk rightly about mathematical ideas, and therefore, how to rightly understand them. As a happy result of that knowledge, students will have significantly less trouble solving individual problems. I'm sure you've seen this in your students as I have mine. I've even found that students with good understanding of the content, will often invent methods much more efficient than methods provided in the textbook. Now, I don't want to completely talk down method. Students simply won't know what to do with their knowledge if they don't have some rote memory and method. It's important. Besides that, there are times where learning a method is necessary before you can come to a fuller realization of a mathematical ideal. Students need to memorize the order of operations. They should know how to perform one division. They should know their trigonometric ratios. But method always needs to take the back seat to content, because methods are man-made algorithms computers can perform, and content is God-given truth, only understandable by language beings. What this looks like in class, I think, can vary, but teaching content over method means, first, that we involve many real-world examples and physical demonstrations, along with verbal explanation. Second, it means using phrases like, a proportion is, rather than, this is how you solve a proportion, especially when students ask for help with specific problems. Guide them to understand the relevant concepts in a problem rather than walking them through an algorithm. Third, teaching content over method means adapting lessons or problem sets within curricula that focus heavily on drilling method. For example, I found Saxon to be very method heavy in lessons and problem sets. Not to talk down Saxon, I love it for its strengths, but I found it's useful to supplement that kind of curriculum. In class, at the very least, we should plan questions for students that get them to ponder the truth of math, not just the tools of math. If the lesson asks students to calculate 23 times 5, I might stop their on-paper calculations and ask, what's 5 groups of 20? And then, what's 5 groups of 3? And then, what's 100 plus 15? Often, conversations like that will produce a couple pairs of wide eyes bright with realization. So, going through math problems verbally like that, I think, is extremely important. Now, I'm aware that many of you don't teach math because you love it, and what I'm proposing sounds like a tall order. What is the true nature of all these mathematical ideas? Or who has time to philosophize about algebra when you have seven other subjects to drop? I want to encourage you that you don't need to be a math nerd to have all the necessary understanding for your math class, especially if you're just teaching your 1 or 2 math classes in the lower grades. In elementary levels of math, you really only need to know the nature of things like the 4 operations, fractions, decimals, and maybe something like negative numbers. Things you're already familiar with. Although, I find division particularly elusive. What is division? For us higher level, these are the things I think of. For us higher level math teachers, though, if math is our thing, we need to pursue fundamental understanding of the less obviously intuitive ideas, like trigonometric functions, square roots, and derivatives, either by reading primary sources, by finding other avenues for further learning, or even just by exploring the math and doing it for ourselves. Besides teaching content over method, I believe there is another concrete way a math teacher can give students understanding through language, and that is by speaking words, by using language. One simple way to do this is to model mathematical thinking by using plain words during instruction, not just symbolic language. For example, I could write something like 3 times x plus 5 in an algebra class. And I could say, okay, we need to use the distributive property to figure this out, and then I need to recall the distributive property and apply it. But it's helpful to say things like, okay, this is 3x plus 5s. And then students will get the idea, okay, this is what the distributive property is actually talking about. If I have 3 boxes of x plus 5s, that means I have 3 x's and 3 5s. So you kind of intuitively get the idea that the distributive property actually works and makes sense intuitively. This is especially valuable in algebra, which without words is prone to become mere symbol juggling. You can also use ample word problems in class, and not just the kind that's easily identifiable as this or that type of word problem. A great source of thoughtful word problems, and a good model for writing them, is Alcuin's Problems to Sharpen the Young. I've included that in your handouts as well. Each problem in this simply lays out a mathematical question in a real-life situation. Some of them aren't so real-life-ish, but you can still relate to them. And it leaves the student to figure it out for himself. The problem doesn't specify this is a sum and some more problem, or find 2 equations to model the situation and solve using substitution. Instead, Alcuin just gives his student a sentence in plain words to work with. You can see a couple of examples of those problems on your handout on the back side there. So one example would be a puzzle called Plowing. How many furrows might a farmer have in each field, the plowman shall have made 3 turns at each end of the field. Like, that's an interesting problem to think about. You actually have to kind of trace it with your finger or draw it out. And there's not necessarily a method to use that they learned. I'll leave you to read the other one. That's a good one too. But there are tons of them in this work. With the student's knowledge of mathematical content and with the guidance of his teacher, the student can find for himself the best method to use in these kinds of problems. One final way we can teach math by language is to use the primary sources. This is the classical way. Western mathematical thought used to be done entirely with words. While words are inefficient, scientifically speaking, they are much more explanatory. Reading a translation of someone like Euclid or Nicomachus forces you to think the way they thought, and it gives insight into what it means to think mathematically, much more than would reading through a symbolic column proof in a modern math textbook. Again, if you can't put it into words, is it really a thought at all? As far as primary sources go, Euclid is a good place to start. And rightfully so, because for many years, the Elements was the geometry, or the math text of the Western world. But I think there are more texts we should consider using, either directly as math classes in themselves, indirectly within other curricula, or even personally, just for our own understanding as math teachers. Apollonius's conics provides fresh new angles from which to understand conic shapes and solids. Nicomachus's Introduction to Arithmetic unveils fascinating patterns and relationships that bring new life to something as simple as the number line. I would add more to the list, but I have primary texts on my bookshelf that I still need to read. A couple would be Fibonacci's Book of Calculations, Newton's Principia, Leibniz's Writings on Calculus, just to name a few. I'm also still searching for some. If anyone knows of more primary math sources, let me know, because I'm trying to find more. I'll be upfront with you and admit that I'm not sure which sources, if any, should be taught in their entirety to, say, a high school class. But I think we need to take seriously the idea of building a curriculum or curricula based on the primary texts of Western mathematics. At the very least, the primary texts should have a significant say in how we teach math. Just like in history, English, or philosophy, to separate ourselves from the mathematical conversation of the West is to jump off the shoulders of giants. So let's work to keep the mathematical language of the past as part of our mathematical language today. To conclude, we are Christian teachers, and that means everything we teach should have Christ at the center, not artificially, but naturally. Realizing what makes a subject Christian will inform how we teach, and math is no exception. If math is the art of navigating the order and beauty of creation through language and wonder, then we should teach math by way of language and wonder. Students can learn to wonder at and wonder about through the 4 mathematical arts. They can learn to rightly speak and think mathematically by learning content and by learning in some fashion the primary texts of Western mathematics. I've come to believe that mathematics taught this way takes into account both the fact that we've been made in God's image and are meant to serve our neighbors, and that our Savior graciously upholds His order in creation for us. Thank you. We've got about 10 minutes for questions, if anyone's got questions or comments or suggestions or simple conversation. Yes?
So, my wife is a math teacher. A number of years ago, she was prepping to teach algebra, and she and I were reading through Euler's algebra. And I've taken math classes before, but the way that totally opens your mind to a new way, it puts you back to before computers were even invented. He doesn't think in decimal terms. he thinks in fractional terms. And now I kind of understand what a logarithm is and what it does and why it's so awesome. Comment on that.
So I actually haven't read that. In fact, I'm going to write that down and add it to my list. Because that sounds fantastic. But that's
Can I be repeated?
yeah. Euler's algebra.
Euler's algebra.
Yeah, Euler's algebra. It's spelled.
We did not finish.
It's not spelled like oil fields. It's spelled E-U-L-E-R. Euler. Yeah, he's definitely a mathematical giant. I appreciate that episode. That would be a great episode. Anybody else? Yeah.
Small word of caution about going back to primary text when it comes to music.
Yes.
One that you are going to encounter is Boethius' De Institutione Musica. While that did have a centuries-long track for being the textbook for music, it unfortunately became obsolete by approximately the 8th century because polyphony was music that he never had to deal with. So if you are applying Boethius to Bach, you're going to have a bad time.
Those sound pretty awful. Yeah, so a lot of that has to do with, I'm assuming you're referencing like the changes in tuning and whatnot that arose from polyphony?
Not necessarily. There's an awful lot that within the range of human hearing can be sonorous within, say, 2 octaves. But once you get to driving the octave out all the way through compounding intervals, say a diapentate, which is a fifth. By the time you go through what we would consider now the circle of fifths, the problem is when you are 7 octaves out, that interval is actually not in tune with the original, and that has to do with a corollary of the rational root theorem, and that's something that he didn't anticipate.
Yeah. So basically, if you're not familiar with the work he's talking about here, and this was the way music was talked about for a long time. What Boethius did in this work, he realized that our musical intervals, so say the fourth, like doo-doo, here comes the bride, or the Star Wars interval, like doo-doo, the fifth, they're based on vibrations happening simultaneously in ratios with each other. So the fifth is a 2-to-3 ratio. So if I had tapped, that's a fifth. Or no, this would be a fifth. But if I sped that up, it would sound like a fifth. So what he recognized was we have these really nice fraction ratios, like 2/3 or 3/4. You get pleasing sounding music with that. But yeah, it doesn't work with polyphony. It starts to sound pretty terrible, at least to our ears, if you start having a bunch of people singing with that particular ratio of harmony. So yeah, that's a good point. I think it's valuable mathematically, just to understand, but yeah, you're right. I would not want to teach that in my music theory class as how tuning works.
So here's your opportunity for wonder at why is that ratio at the end of 7 octaves not in tune?
Yeah.
Oh, Christ who breathed our poison air. Go constant.
Yes.
I'm just curious, do you have like a base curriculum or book that you start with? Because I know a lot of classical schools will use things like Saxon. And I'm starting to not be able to stand Saxon because it's like we're trying so hard to get through all 120 lessons that we don't have time for the wonder and the goodness. And it's like, got to do your 30 questions every night, and everyone hates math by the end of 8th grade.
Yeah.
Well, maybe 3rd grade.
So I use Saxon as well.
Okay.
But and I don't get through all the lessons. I also don't assign all the problems. So, and I think it takes a little work, but you can do that with Saxon, I found, because of the overlap in the lessons.
Yeah, there's some good.
Like if I don't get through math 8-7, Algebra 1 kind of picks up some, or I'm not familiar with the Math 1, 2, 3. Maybe you talk to Eric and yeah, I don't think we should be afraid to cut out some of that for the sake of including some of the wonder. That's a good point.
Following up on that, what would you be happy with having gotten for this year?
I can't say I've been happy with how far I've gotten. So. I've only been teaching math for 3 years, so I don't have a good handle yet, particularly on how far to get in Saxon is necessary. I've gotten through 3/4 of any given curriculum in a year, and it's worked fine because of the overlap, specifically in Saxon. I don't know with other curricula if that would work. Saxon is.
Well, I'm talking specifically with Saxon.
Okay.
I have that same issue where you just feel like you're rushing through everything.
Yeah, I would caution against rushing through for the sake of getting through the book. I've found getting 3/4 of the way through like lesson 90, 100 range. I've found you can usually cover that in the next year if you kind of like figure out which lessons cross over. Yeah.
Yeah, some summer you have some time to look at the table of contents, depending on what lesson you're choosing, or what level you're in. You can. There are lessons that definitely are more stick-worthy than others. And well, and not just what to pick up on next year, but I think too, which ones, because again, as you get through the courses or through the levels, they start to put in all sorts of math that they will eventually get to in high school, but maybe don't need to be explored in those upper elementary and middle school years, and then you can focus more on the wonder of the math at hand.
Yes.
I just want to say I really appreciated your emphasis on language in math, because I feel like what's happening in the public schools is they're doing the exact opposite of that.
Yeah.
And I think it's because the language skills generally are so poor that what they're doing is making it so like getting rid of math problems because they're wanting to just evaluate math rather than English. But I think in doing so, that kind of compounds the problem and makes it worse.
Yeah.
And I think your emphasis on using language, even in math, helps them with understanding language in general, and especially then also understanding math better as well.
Yeah, I think especially in our classical schools where we are making an emphasis on teaching Latin, teaching grammar, logic, rhetoric, teaching good English, it goes right along with that. It's very, very classical. Yes?
Can you repeat your concluding statement on emphasis on navigating?
Oh, yeah. So math is the art of navigating the order and the beauty of creation through language and wonder. Yes?
Can you make your handout available online or something? Because
Sure.
a lot of people didn't get it. We have to pass it around by screenshots.
Write down my email if you'd like. I've got the paper just in written form. Is that the CCLE format? I don't know how that works. Can I just distribute that?
You can distribute.
Okay. So, whoever's on my email, feel free to email me. I can take a transcript or I can give you the handout. Whichever.
True math.
I'm sorry.
That's vocation right there.
Oh, we got a couple more minutes here. Yes?
Just a quick comment on to reinforce your content over method.
Yes.
I was taught one of the ditties of, number, don't be shy, flip yourself and multiply, right? For dealing with the dividing fractions. I studied engineering and realized in helping my own kids with math and going to a math conference that was actually the identity law. Seriously, I did the trick all those years and it worked. So I never wondered, because nobody ever taught me to wonder, so I just did the trick. And I always got it right, so who cared that it was the identity law? But nobody ever explained the laws to me. But I made it through engineering school. Don't do that. Because you can't apply it then in other places. You see what that did? I didn't understand that was the identity law. I couldn't then know how to use the identity law in other places because I only knew how to do the trick.
I think Emily Dickinson has the remedy for that. Tell all the truth, but tell it slant. Success in circuit lies, too bright for our infirm delight, the truth's superb surprise. As lightning to the children eased with explanation kind, the truth must dazzle gradually, or every man be blind.
With that, looks like we're out of time.